Hi, I'm sorry that I couldn't finish that in one video, but it was a nice calculus help session. Sorry you weren't there. Uh, and here we go. So station 11 comes with this picture, and we are given the graph of f prime. These are the slopes of f. This is not f. Okay. F is increasing. Well, f is increasing when f has positive slopes. This is a graph of f prime, the slopes of f. So if f prime has positive slopes when it's increasing, the positive y values here on this f prime graph will be the ones that tell me when f is increasing. So f is, this is station 11, f is increasing on 0 to 1 because these y values are positive on f prime, and 3 to 4 because these y values are positive on f prime, which means f has positive slopes from 3 to 4, and from 4.68 to 5.68, oh, I kind of want to go to 6, yeah, to 6. These are places where f prime is positive, so union 4.6826, and I put a parenthesis here because there's an open circle at 6. When is f decreasing? Well, f is decreasing when f prime is less than 0, and that happens from here to here, so from 1 to 3. No, this is f increasing because f prime is positive. Oh, here's f decreasing because f prime is negative from 4 to 4.68. Union 4 to 4.68. All right, so that's A and B. What the extremes of f of x are? Well, use f prime to determine what the extremes of f are. Yeah, that's a little awkward for me. Do you have a way of knowing that at this point? Oh, yes, you do. Okay. So when I look at this f prime graph, my f prime graph starts at 0, has an intercept at 1, has an intercept at 3, has an intercept at 4.68. And so what do we know? We know that f prime is positive, negative, positive, negative, and then from 5, f prime is positive. So I'm asked for extrema, and I'm thinking, well, hey, so f prime goes from positive to negative. That means f is going from increasing to decreasing. I've got a max at x equals 1 on f of x. I also see over here that I have a max. Do I have a max from 3 to 4.68? No. Sorry, left something out. This is positive. This is negative. 4.68 to 6. Positive. Okay, so max at 1, max at 4. Minimum at 4.68, minimum at x equals 3. Endpoints? Well, let's see. From this point, f increases. So I think there's also a min at x equals 0. It's an endpoint minimum, but yeah, it still exists. And then f prime is positive until 6. So I know that f is increasing, increasing, increasing until we get to 6. So I think that x equals 6 is also a max. Okay, so I've identified where my maxes and mins are. We've got 1. We've got a min at 3. We have a min at 4.68. X equals 0. Yes, and good. Okay, Fabulous. Wait, not 6. Not 6, because there's an, oh, that just means it's not differentiable there. It doesn't mean the function doesn't increase until that point. So I think I'm going to leave that there, but you could probably talk me out of it. Any questions on 11? Okay. What I can't tell you is the value of the mins and maxes. I can't tell you the y value there. That's something that we'll be doing next semester. But for now, let's take a look at station 12. Station 12, hey, didn't we do this problem already? This says f of x equals x over x squared plus 1. I swore we did something like that at the beginning of the stations. No, not that one. No. No. And that one. Oh, negative x over x squared plus 4. So merely similar to this. Okay, so to figure out when this function is increasing or decreasing, I need to look at the derivative of this function. So f prime is going to be 1 times x squared plus 1 to the negative 1. So the derivative of this times this, plus this times the derivative of this. Negative 1, x squared plus 1 to the minus 2. Don't forget the derivative of the inside. Okay, I'm going to factor out that from both of these. So f prime is going to be x squared plus 1 to the negative 2. What's left over? I factored a minus 2 out, so I have an x squared plus 1. Then the plus sign. Now I've got 2x times minus x. That's minus 2x squared. And so if I combine like terms here, I see that f prime is x squared plus 1 to the minus 2, negative x squared plus 1. Okay, so what are my critical values? Well, this thing is never equal to 0. Now we're looking at x squared plus 1. And this parabola never crosses the x-axis. This parabola is never equal to 0. So this part of my f prime is never equal to 0. In fact, it was always above the x-axis. So this is always positive. If I had, say, a minus there, I could say that f prime could be undefined at those places. But no, f prime is never undefined. And this element will always generate a positive number. So I'm going to look over here, and I'm going to set this equal to 0, and I'm going to get minus 1 and plus 1. So when we test 0, I get positive 1, and this is positive. Positive over positive is positive for my f prime sign chart. If I plug in a 2, I'm going to have negative 4 plus 1 is negative 3, but this is always positive. Yeah, no, really, because look, if you plug in a 2, you get 5, and you get 1 over 5 squared, or 1 over 25. See? 25 on the bottom. Positive on the bottom, negative on the top, and that means this is going to be negative. And if I try negative 2, well, these are squaring things. I'm going to get exactly the same values because I'm squaring things. Negative 2 times negative 2 is positive 4, times negative 1 is negative 4, plus 3 is still 1, and I get that. So when is f increasing? F is increasing on negative 1 to 1 because f prime is greater than 0 on negative 1 to 1. Now, then they say, where is f prime decreasing? Well, f prime is decreasing over here from negative infinity to negative 1, union over here, 1 to infinity. That's where f prime, not f prime, where f is decreasing, because f prime is less than 0. Minimum and maximum. Well, when f prime goes from minus to plus, I have a minimum. And when f prime goes from plus to minus, I have a maximum on f. Okay, and I'll let you write those justification sentences. Notice question 3 says, where does f have an inflection point? Okay, so f has an inflection point is going to occur either uh, at the mins and maxes of f prime or when f double prime equals 0. And so I'm about to find f double prime because I don't really feel comfortable graphing this, do I? I don't know, let's see. 1, -1. This is going to be x squared plus 1 squared. Think about it this way. No vertical asymptotes. Y-intercept of 1. 2 x-intercepts. This degree, is much smaller than x to the 4th, so y equals 0. And so I think I got something like that. And so I'm expecting 2 mins and a max. All right, let's see what happens when we do the derivative of the derivative. So I want to do the second derivative. My board needs to be white. F prime was x squared plus 1 to the minus 2, and then negative x squared plus 1. Okay, so let's go with f double prime. F double prime equals f double prime equals, product rule. This times the derivative of that, x squared plus 1 to the minus 2 times negative 2x, plus this, negative x squared plus 1, times the derivative of that. So I bring down the negative 2, I leave the inside alone, I subtract 1, and don't forget the derivative of that inside function, 2x. Okay, so what can we factor out? Well, this to the smallest power, so f double prime, x squared plus 1 to the minus 3. Look, a minus 2x, 2x, and an errant minus. So I'm going to take out a negative 2x as well. And what's left over? Well, I took out that, and I took out minus 3 of those, so I have one of those left over. Now my plus sign. I took out this and this minus and all of this. So I have 2 times these things. It's going to be minus 2x squared and then plus 2. Okay, so that's going to be minus x squared plus 3. And I have minus 2x and x squared plus 1 to the minus 3. All right, there's my f double prime. Now, this is never equal to 0. It's still a parabola shifted up 1. So I don't have to worry about my derivative being undefined. But my second derivative is equal to 0 at 0, and a plus and minus root 3. So x equals 0, and x equals plus and minus root 3. And I'm not sure, but isn't that where we had... yes, these were the places we had mins and maxes on our f prime graph. I graphed the f prime graph, and we saw those 2 low points. These were the mins, this was the max. Okay, and we're looking for inflection points. So let's put these on an f double prime sign chart. We've got 0, we've got minus root 3, and we have plus root 3. Remember, root 3 is like 1.7 something, so here I could do 1 and 2. 1 and 2. And we're plugging these into f double prime. So if I plug in a negative 2, that's going to be 4. That's going to be negative 4 plus 3. That's a negative. Negative 2 times negative 2 is positive, and this is always positive. So negative times positive, which is negative. When I plug in a negative 1, this is now positive. This is positive, because negative times negative is positive. And this is always positive. So I'm going to be positive there. I see a sign change in f double prime. I know that is going to be an inflection point on f. What about plugging in a 1? Well, if I plug in a 1, this is positive, this is negative, this is positive. Positive times negative is negative. And if I plug in a 2, this is negative, this is negative. Negative times negative is positive is positive. And so, yeah, I think those were all inflection points at plus and minus root 3 and at 0. Remember, I have an easier way of saying, in justifying inflection points, there are IPs on f at x equals 0 and x equals plus and minus root 3 because f double prime changes signs at these points. I can't get away with this simplified justification where we just talk about changing signs for maxes and mins because the sign pattern matters for maxes and mins. If this were an f prime sign chart, I'd say a min here, a min here, and a max here because of the pattern in the signs. But I'd have to justify those separately. I'll say, though, you could do the justifications for these not like this, but where you say, okay, there's an inflection point on f at x equals 0 because to the left of x equals 0, f double prime is greater than 0, and to the right of x equals 0, f double prime is less than 0. So you can use that same justification sentence, and I kind of like that one. Like, it works always. It always works for maxes and mins. It always works for inflection points. This only works for inflection points. So if you've got limited capacity in your head to keep all this stuff straight, then don't do this sentence. Instead, do that other sentence, and I'll write it down now for you. There is an inflection point at x equals 0 on f because to the left of x equals 0, f double prime is greater than 0, and to the right of x equals 0, f double prime is less than 0. So you could certainly write that, but remember you have to write it not just for x equals 0, but for also x equals root 3 and also for x equals negative root 3. And that seems like a lot of writing. Okay, 13, our last station. Let's see. So given f of x equals e to the x on 1 to 2, okay, we know what that graph looks like. From 1 to 2, this ordered pair is 2e squared and 1e. All right, what do they want? Find the maxima and minima of f. Well, yeah, so the min is at x equals 1, and then the max is at x equals 2. But notice the question says find the minima and maxima. And so I think in addition to justifying the minimum and maximum, I think I'm actually supposed to say what the value is. Look at the grammar of this statement. Find the minima and maxima of f. Yeah, I don't think it's just where do the minima and maxima occur. Okay, so remember, if I'm looking for mins and maxes, I want f prime equal to 0, I want f prime undefined, and I want endpoints. And we got some endpoints. What about f prime? Well, if f of x equals e to the x, well, we know the derivative of that is itself. Oh, well, this is an exponential growth curve. Here's f prime. And I see that f prime is always positive. F prime never changes signs. My sign chart for f prime looks like this, plus, with no critical points on it. F prime is always positive because f is always increasing. And if f is always increasing, then I don't have that, I don't have that, then my endpoints become the only places to look for maxes and mins. And here with my f prime, I see 1, I see 2, and I say, okay, there's a min at x equals 2 on f of x because to the right of x equals 1, there's a min at 1. To the right of x equals 1, f prime is greater than 0, and x equals 1 is the left endpoint. But yeah, that's only asking the where. I think they might also want to know what is the value of that minimum. So I'm going to plug a 1 into the original function. And I'm going to change this to say there is a min of e to the first at x equals 1. And this f function is increasing until we get to 2, which means that we have there is a max of, well, let's plug that 2 into that function. There's a max of e squared at x equals 2 because to the left of x equals 2, f prime is greater than 0, and x equals 2 is the right endpoint. Okay, make sure you can justify endpoint mins and maxes as well. Using calculus, show why there are no inflection points on f. All right, well, I'm looking for, if I'm trying to find an inflection point, I'm wondering where f double prime changes sign. Okay, and so we know that f is e to the x and f prime is e to the x, and so f double prime would be e to the x, and this is never equal to 0. And if I plug a number in here, I always get a positive. Anywhere on f double prime, I'm going to have a positive value. And because f double prime is always positive, f is always concave up, and therefore f doesn't change concavity. So f is concave up on 1 to 2, since f double prime is greater than 0 always, there is no sign change in f double prime on 1 to 2, so no inflection point. Okay, and then the last question, find the values of c that make the mean value theorem true. And it's interesting because this time we're not asked about the preconditions, but I'm pretty sure you're going to be asked about the preconditions on the AP exam. So please make sure you're comfortable for them. Remember, the mean value theorem says if the function is continuous on the closed interval and differentiable on that open interval, then there must be at least one place called x equals c where the slope of f at c is equal to f of b minus f of a over b minus a. So I'm going to have f of 2 minus f of 1 over 2 minus 1, which is e squared minus e, over 1, which, you could factor an e out, but I'm not sure why you'd do that. So here's the slope of the secant between those 2 points. Now, what am I supposed to do? Well, mean value theorem says that the derivative has to equal this number, this y value at some point. So let's take the derivative of this, e to the x, and set that equal to that. Yeah, okay, got that done. Now what? Well, remember, I'm looking for x. I'm looking for this specific c value. And so what can I do here? Well, I really want to take the ln of both sides. so that this can come down. And I'm taking the ln over here. And so I've got ln of e squared minus e equals c. And that's it. If you decimalize this number, your c is approximately 1.5413. And that's certainly on that interval. Okay, so at this point, the slope on this curve is equal to the slope of that secant line between those two endpoints. All right. Well, you know, the amazing thing is you're going to go take a test on this stuff very shortly. And then we're going to do the second half of Chapter 5. And when we get to the end of Chapter 5, not only will the test contain the material from the second half of Chapter 5, but it will in fact contain this material again. So please make sure you know this stuff. Please make sure if you don't know this stuff, you're asking a hell of a lot of questions. All right, take care.